Hello, ladies and gentlemen, friends and aficionados of pre-calculus and calculus. Welcome to our video lesson today, which is going to tackle the golden ratio. Golden ratio is written as the Greek letter phi. Sometimes if you spell it out, it can be like phi. And then the symbols below here, we have this symbol, kind of a circle with a vertical line segment drawn through it, or this kind of pitchforky sort of thing, except it's not exactly a pitchfork because the right two tines are linked together, but that's how I look at it. And we're going to feature one of my calculus teaching colleagues, fellow YouTuber, Calculus by Christy, and this is her channel. And she, as of current time, has 605 subscribers. And what we try to do with her is we're going to try to see if we can raise her subscribership to greater than 1,000. And I'm sure that when you watch her videos that she'll become one of your favorite YouTubers also. And I encourage you to subscribe to her. I'm going to have a link to her solution to this problem and her channel below. Okay, and her favorite way of doing this, finding phi, the golden ratio, is to use the Fibonacci sequence. And it's since become my favorite way too. The Fibonacci sequence starts out like this: 1, 1, 2, 3, 5, and then you get to the next term by adding the two predecessing terms. So what's 3 plus 5? 8. That's the next term. What's 5 plus 8? 13. What then is 8 plus 13? 21. I think numbers starting to get a little bigger. 13 plus 21, 34, and so on. So it follows this pattern, and what we call these terms are A generically. So any term we can call it A sub n, and this comes from back in chapter 9 in our pre-calculus textbook, which deals with discrete mathematics sequences. And so phi is approximated by taking a term and dividing it by its predecessing term. So phi is equal to the limit as n approaches infinity of a sub n divided by a sub n minus 1. Okay, you don't see the a sub, it's a sub n, little subscript to the right. And in the Fibonacci sequence, as you recall, we added to get something, we found a sub n. It is equal to the sum of its two predecessing terms. So, for example, a sub 34, or a sub n, let's see, this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So a sub 9, we'll say, is 34. Well, a sub 7 plus a sub 8. So it's two predecessing terms. So we call that a sub n minus 1 plus a sub n minus 2. And we can go to our calculator and approximate what phi is. If we take 8 divided by 5, let's go ahead and look at this in our calculator. So if we take 8 divided by 5, clear this off here. Oh, it's behaving wonderfully. Okay, so we say 8 divided by 5. What do we get for that? 1.6. Okay, next one we have 13 divided by 8. 1.625. Next one we have is 21 divided by 13. And lastly, we'll look at 34 divided by 21. And so we can kind of see what these numbers are gradually coalescing toward. It's probably going to end up being 1.61 something, but let's go ahead and go through the exercise here. Now in this first equation we're going to replace that numerator with, we write the same thing here, limit as n approaches infinity of, we replace a sub n in the numerator with a sub n minus 1 plus a sub n minus 2. And our denominator we keep as is, which is going to be a sub n minus 1. Now, what we can do is we can take this first term, a sub n minus 1 over a sub n minus 1, and what does that simplify to? It simplifies to 1. So phi is going to be equal to the limit as n approaches infinity of 1 plus a sub n minus 2 over a sub n minus 1. Okay? Next, we're going to go ahead and work to the right here. And if you notice, phi is going to simplify. It's going to be a term divided by its predecessing term. So we could take this a sub n minus 2 over a sub n minus 1 is going to be approximated not by phi, because phi is going to be a term divided by its predecessing term. Here we're taking a predecessing term, a sub n minus 2, and dividing it by its successive term. So this is going to simplify to, I'm going to come over here, it's going to simplify to theta equals limit as n approaches infinity of 1 plus 1 over phi. Okay, to me this step is the hardest one of the whole bunch. And once you have that, you're able to start working on this. So what we're going to do is we're going to write this out as so this is what it is. We're going to multiply this whole expression here, which is deduced from this limit here, because we have constants. 1 over phi is a constant, so we don't have any variables to substitute n in for. So we're going to multiply this whole expression by phi. So what we get is we get phi squared equals phi plus 1 over phi times phi is 1. And if we subtract from both sides of this equation, we get phi squared minus phi minus 1 is equal to 0. And how are we going to solve this equation for phi? We're going to use something we've done again back in Algebra 2 and in pre-calculus. We use the quadratic formula, and it's negative b, I'm going to put here phi equals negative b plus or minus the square root of b squared minus 4ac over 2a over 2a over 2a over 2a over 2a. So that's what it is right here. And we're going to have a equal to 1. So a is equal to 1. B is equal to negative 1. And C is equal to negative 1. So we're going to enter all these values in here. So phi is equal to better looking phi there for us. It's a little better, okay? So we get negative b, so that's negative negative 1, so it's going to be 1. Let me make some more room below. 1 plus or minus the square root of negative 1 squared minus 4 times 1 times negative 1 over 2 times a, so that's 2. So what that's going to be, it's going to be phi equals 1 over 2 plus or minus square root of negative 1 squared is 1 minus 4 squared. That's going to be 1 plus 4 is 5. So the square root of 5 over 2. And we know that we have to have a successive term to get to the next successive term. Drew the wrong Greek letter there. We need to go ahead and make that positive. So what this means that we can get rid of the negative here. And so that's going to be equal to 1 plus square root of 5 over 2. Now we're going to put that in a calculator, see what we get. Well, calculator tells us one plus, and just notice how close this is to what we did before. Square root of 5 sobre 2. And there we get it, 1.618. Look how close that 1.618 is to our last one, especially the 34 over 21. And as the closer we get out to infinity, the closer we get to the real irrational number phi. The golden ratio. The golden ratio is the pleasing, what looks pleasing, the golden ratio, what a rectangle looks like that's of these dimensions. So that's what is pleasing to the human eye. The Greeks figured out what that was anyway. So that is our answer. And I hope this has been helpful to you. I find this a beautiful little use of limits, kind of merging pre-calculus and calculus. I hope this has been helpful to you. I encourage you to look at Christy's video to see how she did it, and she does it a little bit differently, but again, very worthwhile to subscribe to her channel and support her as much as possible. To one and all, good luck, and as always, thanks for viewing.